Earth is never still. Every second, our planet is rushing through the Milky Way along paths more intricate and mysterious than anything we were taught. If orbiting the Sun is only a thin surface layer, then what is the true journey we are spiraling through in this ocean of stars? This video unlocks that answer with clarity and weight. Share your thoughts on what fascinates you most. For up next is the first part: the real movement of Earth through the galaxy. What if the ground beneath your feet is riding a silent river through the galaxy that never stops? We grow up with the simple picture of Earth circling the Sun, a bright lamp in a dark room. Yet that picture is like a child's drawing of a stormy ocean. Sweet, but incomplete. In truth, our planet is not a calm stone on a fixed track. It is a traveler tucked inside a whole caravan of celestial motion. Earth moves around the Sun. The Sun races through the Milky Way. The Milky Way is pulled by invisible structures on scales so vast that language itself begins to tremble. All of this happens within a universe that is stretching space itself while we sleep. When you stand under the night sky, it feels as if you are still, rooted, secure. But right now, Earth is sweeping along its orbit at tens of kilometers every second. And that orbit is only the first layer of a far richer choreography. The Sun does not sit politely in the center like a king on a throne. It responds to the pull of every planet, especially the giants Jupiter and Saturn. Together with Earth, they all revolve around a shared center of mass, a point floating in space that no eye can see. The result is that our star itself draws a small looping pattern as it drags us through the galaxy. As a scientist, I often think about how misleading the word orbit can be. It sounds like a neat circle on a classroom poster, everything flat and well-behaved. Reality is closer to a spiral staircase that never ends, carved into the fabric of the Milky Way. Our solar system rushes around the galactic center once every few 100 million years, tracing a great ring through a disk of stars, gas, and dark matter. Carl Sagan once said, "We are a way for the cosmos to know itself." If that is true, then our awareness is being carried on a moving platform, a tiny balcony on the rim of a turning galaxy. The Milky Way itself is no island anchored in empty space. It belongs to a small family of galaxies that astronomers call the local group. Most of the time, when we look at the Andromeda galaxy in images, we see a serene spiral hanging in the dark. But in dynamical terms, it is another traveler speeding toward us. Our galaxy and Andromeda are falling together under mutual gravity, an embrace that will tighten over billions of years. Even that is not the end of the story. Both of them, along with dozens of smaller galaxies, are being tugged by a deeper gravitational basin, often called the Great Attractor. A region so crowded with mass that it bends the paths of entire clusters of galaxies. So Earth is not just moving in circles around a star. It is participating in a cascade of motions nested like Russian dolls. Planet around star, star around galaxy, galaxy within a group that is sliding down the slope of some colossal gravity well. All of this unfolds while the universe itself is expanding, not as objects flying through a pre-existing void, but as space stretching between them. Stephen Hawking once pointed out that we are simply advanced breeds of monkeys on a minor planet of a very average star. But we can understand the universe, and that makes us something very special. The irony is that this understanding reveals just how restless our cosmic home really is. If you close your eyes for a moment and imagine time sped up, galaxies no longer seem still. They swirl like luminous leaves in a cosmic current. The Milky Way's spiral arms do not rotate like the rigid blades of a fan. They behave more like waves passing through a crowd. Stars and gas stream in and out of these arms, compressing here, relaxing there. Our solar system glides through these patterns, sometimes wandering into denser regions where supernovae and cosmic rays may be more common. Some researchers have speculated that such passages could subtly influence Earth's climate or even the tempo of evolution. The idea is still debated, but it reminds us that our world is not separate from the galaxy's weather. We are immersed in it. From a personal point of view, this layered movement changes how I feel when I look up at the night sky. The stars are no longer just distant lights sprinkled on a static dome. They are fellow travelers in a vast migration across cosmic time. Brian Cox likes to emphasize that we are part of a dynamic living universe, not observers standing outside it. That thought is strangely calming, even meditative. Instead of clinging to the illusion of stability, we can rest in the knowledge that motion is the natural state of everything from atoms to clusters of galaxies. In such a universe, stillness is not the absence of movement, but the moment when we become aware of it. There is a quiet lesson hidden in all this celestial mechanics. On Earth, we often think in straight lines, beginnings and endings, fixed positions in life. Yet our planet's path tells a different story. We are always in transit, circling, falling, drifting with structures far larger than ourselves. The fact that we can chart these motions, write equations for them, and even predict future encounters between galaxies is a triumph of human curiosity. It means that inside fragile brains made of stardust, the universe has built instruments capable of sensing its own dance. If that does not inspire a kind of cosmic humility, it is hard to know what will. And yet this knowledge is not meant to make us feel insignificant. When you realize that Earth is surfing a web of invisible gravitational threads, your own life can start to look different. Problems shrink a little in scale, but their meaning deepens. Because in all this motion, it is only here on this small world that we have found oceans, forests, languages, and the ability to wonder about our place among the stars. In a universe where galaxies race and space itself stretches, the simple act of pausing to ask where are we going becomes an act of quiet rebellion against indifference. If this slow journey through the hidden motions of Earth makes your mind feel both heavier and lighter at once, you are not alone. Many nights I imagine our planet as a blue lantern hanging from the arm of a moving giant, bobbing gently as it walks through the dark. To follow that lantern with our instruments and our stories is one of the great privileges of being human. If you would like to keep traveling with me through these vast questions, through the science that becomes a kind of bedtime poetry, let your curiosity speak by liking this video, subscribing to the channel, and sharing in the comments what this restless Earth means to you. Because as we continue our exploration, the next step is to look even more closely at that first layer of motion, the one we thought we understood best. The real movement of Earth through the universe that we call home. What if our entire galaxy is not a quiet island in space, but a traveler being pulled and guided by invisible tides through the dark? The Milky Way is moving toward Andromeda at hundreds of miles per second, a giant spiral of stars drifting into a slow and ancient encounter that began long before humans existed and will continue long after our species is gone. Around us, more than 50 other galaxies form the family we call the local group, each one like a lantern in a vast cosmic valley. Yet even this family is not at rest. All of it is being drawn toward a hidden mass in the depths of space, the region we name the Great Attractor, at roughly 373 miles per second. Some astronomers like to say that we are riding on a raft of galaxies swept along by a current we can feel but not yet fully see. When we look up at the night sky, the stars feel still, patient, almost eternal. But that calm is an illusion of our tiny timescale. On human nights, constellations seem fixed. Orion hangs in the same place. The Milky Way arches quietly overhead. On cosmic nights, stretching millions of years, these same stars are rivers of light flowing through the galaxy, and the galaxy itself is flowing through an even greater sea. Some cosmologists like to say that the universe is not a static picture but a choreography, and we are watching a single frozen frame. The approach between the Milky Way and Andromeda is one of the most poetic movements we know in the nearby universe. Two spiral galaxies, each with hundreds of billions of stars, are falling toward each other in a dance that will take about 4 billion years before the first close embrace. To us, that future collision sounds violent, like two cities crashing together. Yet on galactic scales, the space between stars is so vast that most suns will pass by untouched, slipping through like fireflies between trees. What will truly change is the shape of the galaxies themselves, their spiral arms stretched and twisted, their stars flung onto new orbits, until a single larger galaxy is born from the merger. Our descendants, if they exist then, may look up at a very different sky and call that new galaxy home without ever having known another one. This motion toward Andromeda does not happen in isolation. We belong to the local group, a small cluster by cosmic standards, a community of more than 50 galaxies bound together by gravity. Some are large spirals like our own. Some are faint dwarfs, barely visible, even to our best telescopes. Each of them carries its own stars, planets, possibly its own stories of chemistry, and perhaps even life. Yet all of them share one fate: to drift together as a single gravitational family through a much larger structure of galaxy clusters and superclusters. Astronomers sometimes describe this as being embedded in a cosmic web, where filaments of galaxies thread across space like luminous veins in a dark body. The Great Attractor enters this story as a mystery wrapped in gravity. When scientists first mapped the motions of nearby galaxies in detail, they found something unsettling. The galaxies around us were not just moving away, according to the simple expansion of the universe. They seemed to share an extra motion in a particular direction. Our local group, including the Milky Way, appeared to be streaming toward a region in the sky, a patch partly hidden behind the dust of our own galaxy. The mass causing this pull was not immediately visible, yet its gravitational fingerprint was etched into the velocities of thousands of galaxies. One astronomer described it as discovering that your entire town is sliding down a slope you did not know was there, guided by a weight you cannot yet see clearly. Over time, better surveys revealed clusters and superclusters in that direction, including the Norma cluster and the broader Laniakea supercluster. The name Laniakea comes from Hawaiian, meaning immense heaven. It is a reminder that our measurements are not only technical acts but also acts of naming and meaning. Within this immense structure, the Great Attractor is not a single object like a star or a black hole, but a region where mass is concentrated enough to tug on everything around it. Our local group is one thread being drawn into that gravitational basin. And so the Milky Way and Andromeda do not merely fall toward each other. They fall together toward this deeper valley in the landscape of space-time. There is something quietly humbling in realizing that even on the scale of galaxies we are not free. We are not sailing through an empty void by choice. We are being carried by flows of gravity that began in the earliest instance after the Big Bang. Tiny ripples in the density of the young universe grew over billions of years into clusters and superclusters, and those in turn set the paths that galaxies would follow. One physicist once remarked that what we see now is the fossil record of quantum fluctuations written across hundreds of millions of light years. In other words, the reason our sky looks the way it does, the reason we are heading toward Andromeda and beyond toward the Great Attractor, may ultimately trace back to microscopic tremors in the earliest moments of time. From a human perspective, it is tempting to ask what this motion means for us personally. Will the pull of the Great Attractor tear apart our galaxy? Will the approach of Andromeda endanger our sun? The answer, as far as we can tell, is that these motions are grand but slow, powerful but gentle on the scale of a single star system. The tidal forces we feel from these distant masses are real, yet they shape our destiny over billions of years rather than lifetimes. In that sense, they are less like storms and more like the slow drift of continents under our feet, remaking the map in epochs too long for any one civilization to witness from beginning to end. And, yet, emotionally, the knowledge that we are falling with our galaxy toward an unseen basin in the cosmos carries a weight that is hard to ignore. It tells us that our so-called fixed stars are participants in a great river, that our Milky Way is not the center of anything, but one eddy in a larger flow. Some thinkers draw from this a lesson in humility, that our place is small, contingent, embedded in structures far beyond us. Others find in it a kind of quiet comfort, the sense that we are part of a story that began long before us, and will continue whether or not we are here to watch. If you close your eyes for a moment and imagine the scene not in kilometers per second but in feelings, you might picture the Milky Way as a luminous bird gliding through a dark and silent sky. Around it, smaller birds flock and wheel, the members of the local group. Far ahead, barely visible, lies a deeper patch of night where the air seems thicker. That is the Great Attractor. The whole flock moves toward it, not in panic but in inevitability. Our sun is just one feather, our Earth a mote of dust on that feather. Yet from this dust mote arises a mind that can trace the path of the entire flight. When astronomers map these motions with careful measurements, plotting velocities and distances, they are doing more than drawing arrows on a chart. They are slowly revealing the shape of the gravitational landscape we inhabit. Each new survey, each refined distance measurement, sharpens our view of the currents that carry us. In the process, they turn abstract numbers into a narrative, a story in which our galaxy is not static but alive with motion, in which our local group is not isolated but connected to structures so huge that their full extent is still being uncovered. Perhaps the deepest reflection hidden inside all these velocities and directions is this: to understand where we are going, we must first be willing to see that we are moving at all. For centuries, humans believed the Earth was fixed. Then we learned it orbits the Sun, then that the Sun orbits the galaxy, and now that the galaxy itself is swept along by the gravity of even grander structures. Each step has moved us further from the illusion of being at the center, yet closer to a richer truth, that we are threads in a vast fabric, woven by forces that span the whole observable universe. In that sense, the motion of the Milky Way and the local group toward the Great Attractor is not just a fact of astrophysics. It is a meditation on belonging. We belong to our planet, which belongs to a star, which belongs to a galaxy, which belongs to a cluster, which is itself drifting into a deeper, gravitational well we are only beginning to map. To contemplate this is to sit quietly in the middle of a vast moving cosmos, aware that even in stillness, we are always in motion. What is our true speed through the universe? In everyday life, we feel still, anchored to the ground, held by gravity and routine. Yet on the largest stage physics can imagine, we are not calm at all. We are in flight. Not just around the Sun, not just inside the galaxy, but rushing through the cosmic ocean itself with a velocity that only reveals itself when we listen to the oldest light in existence. That light is the cosmic microwave background, the faint afterglow of the Big Bang that fills all of space like a whisper from the first dawn. Scientists discovered that this ancient light is almost perfectly uniform, the same in every direction, like a cosmic choir singing one long steady note. Almost. Because when we point our instruments to the sky with enough precision, we find that the song is slightly louder in one direction and softer in the opposite. That small difference is not a flaw. It is a clue. It tells us that we are moving through this sea of ancient photons, piling up a little more light in the direction of our motion and stretching it in the direction behind us. From this gentle tilt in the temperature of the sky, cosmologists can infer a startling number. The solar system is racing through the universe at about 229 miles per second relative to this primordial glow. This frame, defined by the cosmic microwave background, is as close as we have to a universal reference, a kind of quiet center in the storm where we can measure how wildly we are truly moving. It does not mean there is an absolute rest in the philosophical sense. Relativity still tells us that motion is always about comparison. But if you wish to ask, how fast are we going compared to the average motion of matter and light left from the Big Bang? Then the cosmic microwave background is the calm backdrop against which we draw that answer. George Smoot once described the sky of microwaves as looking at the face of God in a metaphor for how fundamental this radiation is to our understanding of the cosmos. Not as theology, but as a recognition that this pattern of faint light encodes our origin and our movement all at once. To reach that conclusion, scientists had to strip away layer after layer of motion. First, the daily spin of Earth, which makes the heavens appear to wheel overhead. Then the yearly orbit around the Sun, which changes our vantage point in space like a slow, graceful dance. Then the Sun's journey around the center of the Milky Way, carrying us in a broad spiral that takes hundreds of millions of years to complete. And beyond that, the drift of our entire galaxy through the local cluster and toward vast unseen structures whose gravity tugs on us across hundreds of millions of light years. After accounting for as many of these motions as possible, What remains is our net velocity with respect to the sea of cosmic microwave photons. The speed of our small island of stars through the afterglow of creation. When physicists speak about this, their words often carry a quiet awe. Jim Peebles has emphasized that the cosmic microwave background is not just another dataset, but a cornerstone of modern cosmology, a map of the early universe and of our place in it. Brian Greene likes to remind us that the universe gives us both our address and our motion, telling us not only where we are, but how we are streaming through the grand tapestry. And when Stephen Hawking reflected on humanity's ability to understand such things, he pointed out the deep irony that a species so small can nevertheless read the cosmic script written in this ancient light. Their voices together underscore one truth. This velocity is not just a number. It is a revelation about how deeply we are woven into the universe's story. If you close your eyes for a moment, you might imagine that you are sitting still in your chair, your heartbeat slow, your breathing gentle. Yet beneath that quiet, the Earth is turning. The Earth is orbiting the Sun is orbiting the galactic center, and the Milky Way itself is sliding through the cosmic web. All of these motions combine into that single figure measured against the microwave background, like vectors of some grand, invisible geometry. 229 miles each second, every second, without pause. In the time it takes you to take one deep breath, we have already crossed a distance larger than the width of our entire planet. In the space of a lifetime, your body, your memories, your loves and losses are carried across an unimaginable span of the observable universe's fabric. There is a strange comfort in this awareness. For some people, it can feel unsettling to realize that there is no cosmic anchor, no throne of absolute rest where we might imagine the universe sitting still. But for others, this continuous movement becomes a kind of cosmic meditation. We are not trapped in a static prison. We are voyagers. The galaxies are not carved into a fixed crystal. They are part of a flowing pattern of expansion and drift. The cosmic microwave background serves as a reminder that the universe had a hot, dense beginning, and that from that beginning everything has been in motion ever since. Cooling, spreading, evolving. Our measured speed is like a small note in a far larger symphony. Philosophically, this raises gentle questions about identity and perspective. When we say we are moving at a particular speed, what does that really mean for beings who only ever experience relative motion between nearby objects? The answer is that the cosmic microwave background gives us a statistical rest frame, the frame in which this ancient radiation looks the same in all directions. In that frame, the average motion of matter left from the early universe is at peace. Our deviation from that calm is our true cosmic speed. It is as if the universe itself offered us a mirror, and in the reflection we see not our faces, but the streak of our trajectory painted in temperature differences measured to a few millionths of a degree. From a scientific point of view, this measurement tightens our understanding of cosmological models. It feeds into calculations of how structures form, how dark matter and dark energy shape the cosmic web, how galaxies cluster and stream on the largest scales. The dipole pattern in the microwave background, a slightly hotter patch in the direction we are moving, and the cooler patch behind is the simplest feature in the whole sky of primordial light. Yet it encodes our entire local motion. Remove that dipole, and you can study the subtler ripples that reveal the seeds of galaxies and clusters. Keep it in, and you are reminded that your observatory, your telescope, your very planet is part of the ongoing dance. On a more human level, knowing our speed can shift how we feel about our place in existence. Carl Sagan spoke often about the pale blue dot, emphasizing the fragility and unity of life on this small world. If we extend his image, we now know that the pale blue dot is not just hanging in space. It is being carried along a vast invisible current. The fact that we can measure that current, assign it a magnitude, tie it to radiation released over 13 billion years ago, hints at something profound about human curiosity. We are not content to simply ride the current. We want to understand it. As Michio Kaku once put it in his reflections on cosmology, humanity is becoming a species that reads the universe as if it were a book, deciphering its lines of temperature and motion to learn where we are and where we might be going. In the end, the number itself, 229 miles per second, is less important than the story it tells. It tells us that rest is an illusion, that our ordinary sense of stillness hides a deep participation in the unfolding of space and time. It tells us that the afterglow of the Big Bang is not merely a backdrop but a measuring stick, a kind of quiet metronome against which we can time our cosmic flight. And it invites us to see ourselves not as separate from the universe, but as a pattern within it, a brief and delicate structure of atoms riding a beam of motion through the dark. So the next time you look up at the night sky, remember that you are not just looking out. You are looking along the direction of a journey that began long before you were born and will continue long after you are gone. The cosmic microwave background surrounds you, an ancient light against which your existence casts a small, moving shadow. And somewhere in that gentle difference between warmer and cooler patches of sky, the universe is quietly telling you your speed, whispering the simple, astonishing truth that you are always in motion, always traveling, always part of the real movement of Earth through the galaxy and beyond. What if the sun is not a quiet lamp hanging in the sky but a wandering star being carried along a vast river of starlight through the dark body of the Milky Way galaxy itself? When you look up at the night sky, it feels still, patterns of constellations repeating faithfully through the seasons, the same familiar arc from dusk till dawn. Yet in the time-bound chirp mat, gahe mat troi da ditch, quien them hang trem kilometron kongjian lien thien ha. We ride a moving world that circles a moving star that sails through a moving galaxy in an expanding universe. And ho het kuk doi chung ta troi, qua ma hong hei kamnonduk ku truot kong lo do. Astronomers tell us that our Sun orbits the center of the Milky Way at about 143 miles per second. Kang Hern Hai Trum Ba Mui Kilome Moi Giai. At that speed, in the span of a single human heartbeat, Chung Ta Da Dx Ahun, Hiu Rong, Kuamot Fan Fo. To complete just one full circuit around the galactic center takes roughly 230 million years. A so-called cosmic year. When the Sun last passed through this part of its orbit, there were no humans. No Loi Lin Truong, Nu Chung Ta. Chi Ko Hung Long Thong Tri, Tri Dut. Every round trip of our star around the galaxy marks an era change on the grandest calendar imaginable. Carl Sagan once remarked that our galaxy is a kind of city of stars, and we live far from the bright, crowded downtown, somewhere in the galactic suburbs. Our home lies about 25,000 light-years from the center of the Milky Way, nestled in a minor spiral arm called Orion Spur. It is a quiet neighborhood by galactic standards, not too close to the violent heart, where supermassive black holes and dense clusters of stars flood space with deadly radiation. Not too far out where the stellar population thins and fuel for new suns is scarce. Trong Huang Lung Chung A. Ma Tre Kwa Chung Ta, Toi Di Nu. Mot Kiek Thuyen No, Twain Dong Song Sao Le Plan. The laws of gravity give this journey its shape. Deep in the center of the Milky Way lurks a supermassive black hole with a mass of millions of suns. Surrounded by vast swarms of stars, gas clouds, and invisible dark matter, together they weave Mo Trung Hup Dun Kong Lo Keotut Ke, Moi Thu Kwe Kwan. The closer a star orbits to this heavy core, the stronger the pull it feels and the faster it must move to remain on its path. So while our sun speeds along at 143 miles per second, many stars deeper in the galactic city race even faster. Their orbits are tight. Nanage. Nunyung Kiek Xe Lao. Vun Vut Tong Lan Duong. Tong Kung. Kwamot Xa Lo Vuhin. Farther out than us. The traffic slows. The gravitational grip weakens. The astrophysicist Vera Rubin devoted her life to measuring precisely how fast stars circle their galaxies. What she found was shocking. Instead of slowing down in the outskirts, the stars kept moving as fast as those near the center, as if some vast unseen mass was holding them in its invisible hands. From her careful observations was born the modern idea of dark matter, the hidden scaffolding that shapes the rotation of galaxies and the motion of our own sun through the Milky Way. When we say the sun travels at a certain speed around the galactic center, we are really acknowledging that we are bound not only to shining stars but also to a halo of matter no eye can see. Think for a moment about the timescales involved. A human life may last 80 years. Mot kai chirp ma train lich su vutru. In that short span, the sun moves only a tiny segment of its enormous orbit, less than 1 fun mot tria, qua vong tron thien ha. When the dinosaurs roamed the ancient Earth, the sun was on a different stretch of its galactic path. When the first mammals looked up at the night sky with fearful, curious eyes, they were gazing from another point in this slow, majestic circuit. Each layer of fossils buried in our planet's crust corresponds not only to a different era of life, but to a different address along our orbit through the galaxy. Some scientists have wondered whether this grand motion might leave subtle fingerprints on the history of life itself. As the sun glides through regions with more stars and denser gas clouds, our solar system may be exposed to higher doses of cosmic rays or more frequent close encounters with passing stars. Nung shung dong vo hinai kothe kwai dong dam mai sao bang bao quan hei mat tre. Gui nieu thien thach, hon lao vao vung trong, noi tri dut ke vong. Over millions of years, Teng Yet Sak Swert, Vacham Kothe Den Den Tui Chung Hang Lord Wak Mo Duong Chusu Tien Hua Mui. The physicist Adrian Melot once suggested that our path above and below the galactic disk might correlate with some extinction events on Earth, hinting that biology and galactic dynamics are woven together in a subtle cosmic choreography. Yet from our perspective on the ground, everything feels calm. The sun rises, sets. Tre lai kung mot kung tre. The constellations appear fixed, their mythic figures frozen in place. This tranquility is an illusion born of our smallness. It is like sitting on a smoothly gliding train at night, watching distant lights drift by and feeling as though only the world outside is moving. Galileo understood this centuries ago when he wrote about the relativity of motion. explaining rang kong ko he kui kio twit doi nao de noi kai ji thuksu dong yen. Chi ko kai nai chuyen dong so vai kai kash. Our sense of rest is simply our brain choosing the local frame of reference and ignoring the deeper tides that carry us all. To visualize the sun's path through the galaxy, many scientists use the image of a spiral. We are not tracing a simple flat circle, but a gently bobbing wave that threads its way around the galactic center, while the spiral arm itself also evolves. The Milky Way rotates like a vast pinwheel, but the spiral arms are more like patterns of traffic density than rigid structures. As density waves sweep through the disk, gas clouds are compressed, new stars ignite, old ones drift out again. Our sun likely formed in such a wave billions of years ago. Now it carries its planets with it, weaving a corkscrew trail through the interstellar medium, leaving behind subtle traces in magnetic fields and diffuse gas. Stephen Hawking once said that we are just an advanced breed of monkeys on a minor planet of a very average star. But we can understand the universe, and that makes us something very special. To grasp the true movement of the Sun and the solar system through the Milky Way is to feel both halves of that statement at once. On the one side, we realize how unremarkable our star is among hundreds of billions. Circling a center it will never reach in a lifetime of galaxies. On the other, we are a species capable of measuring speeds in miles per second across tens of thousands of light years, capable of building maps of a galaxy we have never left. Trong do sao vo min qua vu tru. I thuk no benai, lai tre than diu fi thuong. When you stand under a clear sky and feel the cool air on your skin, you are not standing still. You are being carried on a spinning Earth, orbiting a moving sun, circling a galactic center wrapped in dark matter. At about 143 miles every second, the solar system glides forward, never to return to exactly the same place again. The stars ahead of us are strangers we have not yet met. The stars behind us are neighborhoods we left hundreds of millions of years ago. Perhaps that is the quiet meditation hidden inside these cold numbers. Our lives are short, our stories fragile, but they are written on a world that is endlessly journeying through a galaxy alive with motion. To know this is to feel a mixture of humility and wonder. We are passengers on a luminous ship sailing through a sea of darkness. And for a brief moment, Chung ta du tin tao, de nyon ra han, tring a. What if the solar system is not gliding gently through the galaxy at all, but bobbing up and down like a small boat on a slow and ancient cosmic tide? What if every rise and fall of our sun through the dark galactic sea quietly rewrites the story of life on Earth? Astronomers have learned that the orbit of the sun around the center of the Milky Way is not a perfect flat ring, not a neat track on a gigantic celestial racetrack. Instead, our star moves in a great wave-like motion, drifting above and below the thin disk of stars and gas that we call the galactic plane. It is as if the sun is breathing in the vertical direction, inhaling and exhaling over tens of millions of years. One full breath takes roughly 60 million years, a time scale so large that entire mountain ranges rise and erode while the solar system merely completes a single oscillation. Right now, the best models suggest that we are not exactly in the middle of the disk, but a little above it, only a few tens of light years away from the imagined mid-plane where matter is densest. From our human point of view, that distance is beyond comprehension. From the galaxy's point of view, it is just a tiny step upward on a much larger path. The Milky Way disk is hundreds of light-years thick in stars and thousands in its more tenuous components. And within that thickened sheet, the sun is like a grain of dust caught in a slow vertical vibration. Why does this up and down motion happen at all? The answer lies in gravity and in the way mass is spread through the galaxy. The disk of the Milky Way is not empty. It is filled with stars, gas clouds, star clusters, and something even more elusive called dark matter. All of this mass acts together to pull objects back towards the midplane. When the sun drifts above the disk, gravity tugs it downward. It gains speed, crosses the center, overshoots into the region below, slows again, and is tugged back once more. The result is a gentle but relentless oscillation, a vertical heartbeat of our orbit around the galaxy. In this picture, the solar system is not a fixed platform for life. It is a moving stage, slowly passing through different neighborhoods of the Milky Way. Some neighborhoods are quieter, with fewer nearby stars and less dangerous radiation. Others are busier, packed with dense star fields, powerful ultraviolet light, and the shock waves of ancient supernovae. As the sun approaches the crowded central regions of the disk during the lower part of its oscillation, the environment may become harsher for any fragile biosphere clinging to a small rocky world like ours. This is where the story becomes darker and more intimate at the same time. Over the past century, geologists have mapped mass extinctions in Earth's fossil record. Times when a large fraction of species disappeared in what looks like a geological instant. Some researchers have noticed that these great die-offs seem to show a rough rhythm, a pattern with gaps of tens of millions of years. Out of this observation grew what is sometimes called the Shiva hypothesis, the idea that periodic upheavals in life on Earth might be linked to the solar system's vertical journey through the galactic disk. According to this suggestion, when we pass close to the midplane where stars and dark matter are densest, the gravitational pull of the disk on distant icy bodies in the outer solar system increases. A slight extra tug on the vast cloud of comets surrounding us could be enough to dislodge some of them and send them spiraling inward towards the sun, turning the quiet inner system into a shooting gallery of long-period comets. Over millions of years, an increased bombardment might raise the probability of catastrophic impacts on Earth, leaving behind craters and extinction layers in the rocks. The galaxy itself would become an unseen player in Earth's biological drama. Not everyone agrees that the numbers line up perfectly. Some studies find a periodicity in the extinction record. Others see more noise than pattern. Yet the idea that our planet's biosphere might be sensitive to the slow dance of the solar system through the Milky Way has a deep emotional pull. It suggests that dinosaurs, ancient forests, coral reefs, and even humans are caught in the same large-scale movement as our star, rising and falling together through the disk like passengers in a cosmic elevator whose music we can barely hear. Carl Sagan once wrote that we are a way for the cosmos to know itself. In the context of this vertical oscillation, the phrase takes on an almost haunting flavor. We are not just observers standing outside the experiment. We are part of the moving apparatus. The same gravitational field that shapes our sun's path through the disk shapes the deep time of life on Earth. The rocks in your hand, the fossils in a museum, and the quiet breath you take tonight under the stars may all be faint echoes of where the galaxy has carried us in ages long past. Modern physicists like Brian Cox often remind us that we are the universe made conscious. When we map the Sun's orbit in 3 dimensions and trace its slow vertical wave through the galactic plane, it is really the galaxy drawing a diagram of its own structure through our minds. We use equations and observations, but underneath the mathematics lies a very human feeling, a mixture of smallness and belonging. Small, because our entire history fits into a tiny fraction of one oscillation cycle. Belonging, because that same cycle cradles us in its regularity. Imagine deep time not as a straight line, but as a slow vertical wave. At one crest, early life struggles in ancient seas, while the solar system glides calmly above the plane. At another, passing through the mid-plane, comets rain more frequently and ecosystems shudder. Much later, on another gentle rise, a species able to build telescopes and accelerators appears, just in time to realize that the galaxy might have been nudging its world all along. If this story is even partly true, then our curiosity about the galaxy is not a luxury. It is a survival instinct stretched over millions of years. There is also a quieter, almost meditative way to hold this knowledge. When you look up at the night sky, you are not beneath a static dome of stars. You are inside a moving river of light, carried upward through the disk of the Milky Way on a journey you did not choose, but that you are invited to witness. The familiar constellations are temporary arrangements, slowly warping as stars drift, while the whole sheet of the galaxy itself curves around us, tugging gently at our orbit. Knowing this, it becomes harder to feel completely detached from the rest of the cosmos. The idea that oscillations through the galactic plane might be connected to mass extinctions will continue to be tested and challenged. New data on crater ages, fossil diversity, and the detailed distribution of matter in the Milky Way will refine or perhaps overturn the Shiva-style scenarios. That is how science breathes, by rising towards new hypotheses, then falling back through careful criticism and evidence. But even if the exact link between vertical motion and extinction proves weaker than some hope, the larger insight remains powerful. Life on Earth does not evolve in isolation. It unfolds within a changing galactic environment. In the end, the Sun's gentle bobbing above and below the galactic plane invites a different way of seeing ourselves. We are not just residents of a small blue world near an average star. We are travelers bound to a slowly breathing orbit within a spiral galaxy. Our myths speak of cycles of death and rebirth, of ages that rise and fall. And here in the mathematics of stellar dynamics, we find a distant mirror of those stories. Perhaps that is the hidden gift of this knowledge. Not only that, it might help us understand ancient extinctions, but that it allows us to feel the rhythm of the Milky Way in the long, quiet heartbeat of our own world. What if the Milky Way is not a frozen pinwheel in the sky, but a living ocean of waves that quietly shapes the fate of life on Earth? When we look up, we see a soft river of light, a pale band crossing the night like a memory half remembered. To the naked eye it seems calm, eternal, a backdrop against which the small drama of human lives plays out. Yet hidden inside that gentle glow is motion, pressure, rhythm, the slow heartbeat of spiral arms drifting through the dark. Astronomers call it the density wave theory. But underneath the technical name lies a simple image, like cars bunching up in a traffic jam while the road itself stays in place. The stars and gas are the cars. The spiral arm is the jam. Matter flows in, slows, brightens with new stars, then flows out again. And, somewhere inside one of those waves, very quietly, our sun is passing through. In this picture, the spiral arms are not rigid structures painted onto the galaxy. They are patterns of crowdedness moving through a disk of stars and gas. Like ripples traveling across the surface of a pond, the waves slide around the galactic center at their own speed, different from the speed of individual stars. The sun, like a swimmer in a slow tidal current, feels the gentle pull of these crowded regions as it orbits the core every few 100 million years. Each time we drift into a higher density zone, the sky around us changes in ways we cannot see with human eyes. There are more stars nearby, more supernova remnants, more invisible shock fronts, and with them come messengers even finer than starlight, the high-energy particles we call cosmic rays. Cosmic rays are born in violent places, the aftermath of exploding stars, the jets of black holes, the shock waves in turbulent clouds. They streak through the galaxy at nearly the speed of light, threading the vast spaces between suns. Most of the time, Earth is shielded by its magnetic field and by the sun itself. But if we travel through regions where stars die more often and supernovae fill space with fresh radiation, then the background drizzle of cosmic rays that reaches our atmosphere can subtly change. Some researchers have wondered whether these changes are written into the rocks and fossils of our planet, like a secret code linking the dance of the spiral arms to the history of life. Astrophysicist Nir Shaviv has argued that there may be a connection between our passage through denser spiral regions and cycles of climate and extinction on Earth. It is a controversial idea, and like all bold proposals in science, it stands in a field of doubt and careful testing. Yet even the possibility is haunting, that when Earth crosses a crowded lane of the galaxy, the sky grows subtly harsher, and the shower of cosmic rays thickens. Some models suggest that increased cosmic rays could change the rate at which clouds form in the lower atmosphere, nudging the climate toward cooler or warmer states over millions of years. Others ask whether bursts of radiation might alter DNA mutation rates, speeding up evolution in some epochs and slowing it in others. We do not yet know how strong these links truly are, but the questions themselves reshape our sense of home. As Nobel laureate James Peebles once said, "We are trying to understand not just the contents of the universe, but its story." The spiral arms and their density waves are one chapter in that story, a chapter where gravity, time and motion write patterns across hundreds of thousands of light years. In the quiet language of physics, a density wave is simply an oscillation in mass distribution. In the language of a wandering species on a small blue world, it is a slow turning page that may decide when ice sheets grow, when forests spread, even when certain branches of life flourish or fade. Seen from far above, the Milky Way would look like a vast luminous whirl, arms curling outward from a bright central bulge. Yet even this image is a kind of illusion, because the arms are not made of the same stars forever. Stars drift in and out, like lanterns carried by a crowd walking through a foggy street. Our sun was not born in the same arm where it now resides, and it will not remain here for the rest of its life. Over hundreds of millions of years, its orbit slowly cuts across these waves. Sometimes we ride just behind the crest, in regions of active star formation. Sometimes we fall into quieter inter-arm space, a darker corridor where massive stars are rarer and the sky is a little less violent. The gravity of neighboring galaxies adds another layer to this subtle choreography. The Andromeda Galaxy, our great companion in the local group, exerts a distant pull on the Milky Way. Smaller satellite galaxies tug at the outskirts of the disk, stirring its stars and gas. These encounters can reinforce or disturb the spiral pattern, like a passing ship sending waves into an already restless sea. Some simulations show that flybys and minor mergers can trigger new spiral arms, or amplify existing ones. So, when we speak of density waves, we are not talking about a single isolated mechanism. We are listening to the combined music of gravity from many sources, playing over billions of years. The sun rides through this galactic weather, carrying with it a fragile bubble of influence, the heliosphere. It is formed by the outflow of the solar wind, a continuous stream of charged particles that pushes back against the surrounding interstellar medium. When we enter a region of higher gas density, or stronger external magnetic fields, the heliosphere can shrink or change shape. That in turn affects how many galactic cosmic rays can leak into the inner solar system and reach Earth. In this way, the slow breathing of the spiral arms and the tug of neighboring galaxies may modulate the invisible rain of particles that falls through our atmosphere every moment. Inside that atmosphere, in the layered shell of air hugging our world, every cosmic ray that strikes can start a small cascade. Particles collide with molecules of nitrogen and oxygen, triggering showers that branch and fade. Some ionize the air, creating charged seeds around which tiny droplets of water can form. The idea that this process might influence cloud cover is still debated. Clouds are complex, sensitive to many factors, from aerosols to temperature gradients to ocean cycles. Yet it is striking to imagine that as the Milky Way's spiral pattern turns, it might gently adjust the fabric of our weather, not in days or years, but across epochs and ages. Life itself is a recorder of such changes. Fossil layers, ice cores, sediment beds on ancient seafloors all carry signatures of shifting climate and radiation. Some periods show higher extinction rates, sudden turnovers in which many species vanish while others appear and spread. Scientists have proposed many causes, from volcanic eruptions and asteroid impacts to continental drift. To this catalogue of earthly forces, the idea of spiral arm passages adds a cosmic dimension. Perhaps once in a great while, as we cross a bright, crowded lane filled with dying stars, the background level of stress on living systems rises just enough to tip the balance. Not as a single catastrophic event, but as a slow sharpening of the environment, a tightening that lasts for millions of years. Astrophysicist Carl Sagan used to say that we are star stuff contemplating the stars. In the context of spiral arms and density waves, the phrase takes on a deeper shade. We are not just made of stardust. We are shaped by the long-term weather of our galaxy. The pattern of arms, the timings of their waves, the quiet intervals between them may all be woven into the story of forests, oceans, and even human consciousness. To sit beneath the night sky and feel a breeze, to watch clouds move across the moon, is, perhaps, to feel faint echoes of decisions made far away by gravity and time. And yet, for all this grand interconnectedness, there is humility in what we do not know. Many details of spiral structure are still under active study, from the exact pattern speed of the arms to their longevity and origin. Observations from radio telescopes, infrared surveys, and the precise stellar maps of missions like Gaia are slowly sharpening our view. Brian Cox has remarked that science is not about certainty. It is about the most reliable way of thinking about the world. In that spirit, the idea that spiral arms influence climate and evolution remains a possibility, a hypothesis tested against data, revised as new evidence arrives. But whether the link proves strong or weak, the larger insight endures. We do not orbit the sun in isolation, like a lone bead on a wire. We move inside a galaxy of waves, tides, and distant tugs. Our history is nested in larger histories, our cycles in deeper cycles that span the disk of the Milky Way. To contemplate the spiral arms and their density waves is to feel time stretch, not in years or centuries, but in revolutions of an entire galaxy. Perhaps that is the quiet gift of this perspective, that as we breathe in the thin air of Earth, we are also breathing with a living, turning, evolving cosmos. Have you ever wondered why the sun is actually closest to Earth in the deep of northern winter? Why the point of greatest warmth in our imagination does not match the point of greatest proximity in space? The quiet secret is that our planet does not follow a perfect circle. It moves along an ellipse, softly stretched in the darkness. And this gentle imperfection shapes the rhythm of our seasons in ways both subtle and profound. Astronomers call the closest point of this path perihelion, a word that means near the sun. And for Earth it arrives around the 3rd of January each year. The farthest point is aphelion, when we are slightly more distant around the 4th of July. To the human heart this might feel backwards. The north wrapped in cold when we are nearest to the star that gives us life. The north bathed in warmth when we are at our most distant. Yet the cosmos often speaks in paradoxes. And this one is resolved once we remember that it is the tilt of Earth rather than the distance to the sun that rules the seasons. Our world leans by a little more than 23 degrees relative to its orbital plane. And that tilt decides whether sunlight strikes a hemisphere head-on or only grazes it. As the physicist Brian Cox likes to say, the seasons are really about geometry rather than how close we are. In January, the northern hemisphere is tilted away from the sun. Light arrives at a shallow angle. Days are short. And the cold deepens, even though our planet has drawn slightly nearer in its elliptical sweep. In July, the north is tilted toward the sun. Sunlight falls more directly. Days stretch long into evening, and warmth fills land and ocean while we are a little farther from the stellar fire. Johannes Kepler was the first to grasp that planets trace ellipses rather than circles around the sun, and he called this insight a gift wrested from the book of nature through years of patient struggle. His first law of planetary motion quietly governs every dawn and dusk you have ever seen, every sunrise by the sea, every evening when the sky fades from blue to deep violet. Isaac Newton later showed that an ellipse is the natural path for bodies bound by gravity and set in motion, a conversation between mass and movement that plays out in slow elegance over millions of orbits. When we speak of perihelion and aphelion, we are really reading the punctuation marks of that ancient conversation. Although the difference in distance between these 2 points is only a few million kilometers compared to the vast average distance to the sun, the change is still measurable and real. Earth receives slightly more solar energy at perihelion than at aphelion, and our climate system responds like a great breathing lung. Oceans absorb and release heat slowly. Continents react more quickly. Ice and clouds scatter sunlight back into space. The result is that patterns of wind, storm tracks, and monsoon rains carry faint signatures of this elliptical rhythm, even though the dominant melody is still written by the tilt and piece, the distribution of land and sea. In the southern hemisphere, this subtle difference can be felt a little more clearly, because perihelion aligns with their summer months. Slightly stronger sunlight arrives when the south is tilted toward the sun. And over the great spread of the southern oceans, this can enhance temperature contrasts and storm activity in ways that climatologists continue to study. It is as if the ellipse adds a soft accent to the seasonal music, a gentle emphasis rather than a complete change of tune. Modern climate science also reminds us that Earth is not a static machine. Its orbit, its tilt, and even the direction of that tilt slowly change over tens of thousands of years under the pull of the Moon and the other planets. These shifts are known as Milankovitch cycles, named after the Serbian mathematician Milutin Milankovitch, who devoted his life to understanding how orbital variations could pace the advance and retreat of great ice sheets. During some epochs, perihelion has occurred closer to northern summer, at other times closer to northern winter, and these shifts have subtly altered the contrast between seasons. Over many cycles, ice ages have bloomed and faded as sunlight distributions changed, showing how something as quiet as the shape of an orbit can steer the fate of glaciers, coastlines, and ecosystems. Carl Sagan once reflected that our understanding of planetary orbits is a testament to the power of human reason. That from a small world under a bright sky we have managed to decode the dance of worlds themselves. When you stand outside on a clear morning and feel the low sun of winter or the high arc of summer, you are not only feeling weather, you are sensing geometry in motion. The angle of light on your face, the length of your shadow on the ground, the way frost lingers or vanishes, all are local expressions of our global path around the sun. If you could watch Earth from far above the solar system, you would see a small blue world tracing its elongated loop, moving a little faster near perihelion and a little slower near aphelion. Kepler described this change in speed in his second law, noting that a line from planet to sun sweeps out equal areas in equal times. To a distant observer, this would look like a graceful acceleration and deceleration, as if Earth were breathing in near January and breathing out near July. Down here on the surface, we do not feel this change as motion, yet its imprint is everywhere in the timing of seasons, in the chronology of migrations, in the life cycles of forests and coral reefs. Thinking about this path can also be strangely calming. In a universe that can seem chaotic, Earth follows a pattern that is both precise and forgiving. The ellipse is stable enough to cradle the evolution of life over billions of years, yet flexible enough to allow the slow drift of climates and habitats that drive adaptation. We live within a balance between nearness and distance, between the intimacy of perihelion and the cool detachment of aphelion. Each year this balance resets, offering another cycle of cold and warmth, dormancy and growth, night that stretches and then recedes. As you listen to the story of Earth's elliptical orbit, you might notice a subtle shift in perspective. Our planet is no longer just a backdrop for weather reports and calendars. It becomes a traveler with a slightly eccentric stride, a being whose path has texture and character. The words perihelion and aphelion stop feeling like technical jargon and begin to sound like chapters in an ongoing journey. And in that journey, the gentle differences in distance and timing become part of a larger cosmic meditation on how small variations can echo through deep time. So when someone tells you that Earth orbits the Sun, you now know that the truth is richer. It does not simply circle. It glides along an ellipse, drawing near in the quiet days of early January and drifting farther in the bright height of July. That small asymmetry shapes currents in the air and sea, helps nudge climates over vast spans of time, and reminds us that perfection in nature is rarely a perfect circle. In the gentle stretch of that orbit, our seasons find their cadence, and our lives unfold within a dance of light and distance that has been repeating long before the first human ever looked up and wondered why winter and summer feel so different. What if the sun itself is not the calm center you were taught it to be, but a dancer being pulled off balance by two giant partners called Jupiter and Saturn? From very early on, we imagined the solar system as a tidy clockwork, the sun nailed to the center, the planets circling like obedient beads on invisible strings. Yet, when astronomers began to trace the motion of the sun with greater precision, they discovered something unsettling and strangely beautiful. Our star does not sit still at all. It wobbles, loops, and drifts around a shifting point in space known as the barycenter, the true center of mass of the solar system. Jupiter, with its enormous bulk, and Saturn, with its ringed gravity, do not merely orbit the sun. They pull the sun toward them so strongly that the whole system becomes a slow cosmic dance rather than a simple spinning wheel. Isaac Newton once reflected that every action of gravity is mutual and exact. The Earth pulls the apple as surely as the apple pulls the Earth. In that same spirit, Jupiter and Saturn pull the sun as surely as it pulls them. And this reciprocity writes subtle patterns into the space through which Earth must travel. When we say the sun moves around the barycenter, we mean that the combined gravity of all the planets shifts the effective center of the system away from the sun's heart. Sometimes this center lies inside the sun, sometimes outside it, and the star traces looping paths around that invisible point, like a lantern carried in a slow spinning dance. Jupiter contributes the lion's share of this pull. Saturn adds another deep note, and together they produce long cycles in the motion of the sun that can last decades and centuries. These motions do not fling Earth wildly across space, yet they gently perturb our orbit, turning what might have been a simple ellipse into a shape that breathes in and out over long spans of time. In celestial mechanics, this gentle nudge is called a perturbation. It sounds small, almost harmless, but nature has a habit of letting small things accumulate, especially when they repeat with patient rhythm. Each time Jupiter and Saturn line up in certain ways, their combined gravity tugs a little harder on Earth and on the Sun, shifting angles and distances by amounts too tiny to feel in a single human lifetime. Over tens of thousands of years, though, these changes can add up to alterations in the shape of our orbit and even the tilt of our axis relative to the Sun. The great mathematician Pierre-Simon Laplace once described the solar system as a kind of grand mechanical poem, where every inequality and small deviation has a story and consequence. Those inequalities include the way Jupiter and Saturn slowly trade energy with the inner planets through resonance, like musicians, passing a theme back and forth in a long unfolding symphony. As these gravitational themes repeat, the distance between Earth and the Sun at different points in the year shifts. The eccentricity of our orbit varies, and the way sunlight is distributed across latitudes gradually changes. Climatologists and astronomers link some of these long-term variations to what we call Milankovitch cycles, slow changes in Earth's orbit and tilt that affect the rhythm of ice ages and interglacial warmth. The giants are not the only cause, but their mass makes them key players in this ballet. Over about 100,000 years, the ellipticity of Earth's orbit breathes in and out, bringing us slightly closer or farther from the Sun in different seasons. Over roughly 41,000 years, the tilt of our axis rocks between smaller and larger angles, changing how harsh winters are and how far summers reach toward the poles. Jupiter and Saturn, with their ceaseless pull, feed these cycles with tiny gravitational investments that pay out over geological time. Carl Sagan liked to remind us that worlds are shaped not only by cataclysms, but by the gentle tug of distant bodies over eons. In that spirit, every small deflection in Earth's orbit is a quiet sentence in a story about oceans freezing or thawing, forests advancing or retreating, species emerging or disappearing. When the giants shift the Sun a little and bend Earth's path a little more, they are in effect modulating the cosmic spotlight that warms our world, painting slow-moving patterns of climate across the ages. If you could watch the solar system from high above the galactic plane sped up across millions of years, you would not see neat circles. You would see spirals within spirals, loops layered upon loops. The Sun sketching corkscrew paths around the barycenter, while the planets weave in and out like fireflies around a drifting lantern. Earth in that picture is not merely a follower. It is a small dancer responding to the shifting center of gravity beneath its feet. Sometimes the path brings it fractionally closer to the Sun at key seasons, sometimes fractionally farther. Across deep time, these fractions matter. Glaciers may march or melt a little sooner. Rain belts may drift. Deserts may widen or shrink. Modern astrophysicists who study planetary dynamics often speak with a mixture of respect and humility about these effects. Brian Cox has remarked that our climate and even our history are written in a dialogue between starlight and gravity. Jupiter and Saturn give gravity its deepest voice in that dialogue, answering the Sun's steady pull with their own low booming chorus. The result is not chaos, but a richly textured order, an order that includes room for surprise. One might ask whether these distant tugs could threaten stability itself, whether the giants could one day toss Earth into some catastrophic new orbit. The calculations reassure us. The inner planets move in a system that is largely stable over billions of years, yet not perfectly so. There is a fine balance between predictability and sensitivity, a reminder that even in a mostly orderly cosmos, nothing is completely fixed. Michio Kaku has compared the solar system to a long-running symphony where a single off note rarely ruins the piece. But over vast durations, the themes can slowly shift in unexpected ways. In our daily lives, none of this is visible. The sunrise appears punctual, the seasons familiar, the stars above steady in their constellations. Yet behind that apparent constancy there is the ceaseless work of those giant planets carving faint grooves into the fabric of our orbit, pushing and pulling the Sun so that the true center of our motion is always just slightly elsewhere. To meditate on this is to feel both smaller and more deeply connected. Smaller because our world is not the solid anchor we once imagined. More connected because our climate, our history, our very existence are intertwined with worlds we will probably never set foot upon. When you look up at Jupiter shining bright in the night sky, or trace the delicate ringed glow of Saturn through a telescope, you are not just seeing distant ornaments. You are seeing two of the silent authors of Earth's past and future. Vera Rubin, who helped reveal the hidden mass of galaxies, reminded us that the universe is far more dynamic than its calm appearance suggests. In the same way, the solar system you learned as a child is more alive and more intricate than a static diagram can show. Perhaps the most humbling thought is this. As Earth drifts through these subtle gravitational currents, life continues to adapt. Civilizations rise and fall. And we stand here just long enough to notice that somewhere far away, two giant worlds are quietly rewriting the long, slow choreography of our seasons. In the background, the sun keeps burning. The barycenter keeps wandering. And our planet keeps following its gently perturbed path through the dark. To sit with that image is a kind of meditation in itself. A reminder that we are passengers not only of one star but of a whole gravitational conversation whose sentences are measured in millennia. And while we may never feel the pull of Jupiter and Saturn in our muscles or our breath, we live inside their influence all the same. What if the rhythm of Earth's climate is not random at all, but the slow breathing of a planet obeying the geometry of the sky? Long before humans burned their first piece of coal, Earth was already moving to an ancient beat, a cycle written in the tilt of its axis, the elongation of its orbit, the slow wobble of its spin. These are the Milankovitch cycles, named after the Serbian mathematician Milutin Milankovitch, who spent years of his life calculating how tiny changes in sunlight over tens of thousands of years could summon and dismiss whole ages of ice. He once wrote that the history of climate is inscribed in the heavens. And when you follow his reasoning, you begin to see Earth not as a fixed blue marble, but as a pilgrim turning its face toward and away from the sun in slow, deliberate arcs. Imagine the axis of Earth not as a rigid spear but as a gently nodding head, bowing and lifting over cycles of about 41,000 years, sometimes tilted a little less, around 22 degrees, sometimes a little more, around 24.5. This small change in tilt seems almost trivial on human timescales, yet it reshapes the map of sunlight on the planet, altering how much energy the polar regions receive in summer. When the tilt is greater, summers at high latitudes are warmer, winters are colder. Ice finds it harder to survive those bright, intense summers, and great ice sheets retreat. When the tilt relaxes and the axis leans less, summers in the far north become cooler and more timid, allowing winter snow to linger, compressing layer upon layer into the slow armor of ice that can bury continents. Brian Cox once said that climate is the story of sunlight spread in space and time. The Milankovitch cycles are the geometry behind that story. They do not change how much total light the sun pours out, but they endlessly shuffle where and when that light falls. The orbit of Earth is not a perfect circle. It gently stretches and relaxes over cycles of about 100,000 years, becoming slightly more oval then more round again. In the more elongated phases, the difference between closest and farthest distance from the sun grows, and with it the contrast between the seasons in one hemisphere compared to the other. Layered on top of this is the slow wobble of the axis itself, a motion called precession, like a spinning top that traces a circle in the air as it turns. Over about 23,000 years, this wobble changes the timing of the seasons along the orbit, so that the moment of closest approach to the sun can occur during northern summer in one epoch and northern winter in another. The French glaciologist Claude Lorius, who read the ancient air trapped in Antarctic ice, once noted that the dance of these cycles matches the coming and going of ice ages with uncanny precision. It is as if the great ice sheets are instruments, and the orbital cycles are the slow musician, plucking and releasing notes over hundreds of centuries. When these cycles combine in certain configurations, the result is a subtle reduction in summer sunlight at high northern latitudes, particularly around places like Canada and northern Eurasia where large landmasses allow snow to accumulate. A few summers in a row that fail to fully melt the winter snow, and a thin white blanket becomes a thicker one, reflecting more sunlight back into space, cooling the region further. Over thousands of years, this feedback can transform a landscape of forests and rivers into a realm of flowing ice, carving valleys, damming lakes, displacing whole ecosystems southward. The record in ocean sediments and ice cores shows this pattern like a heartbeat. Advance and retreat, freeze and thaw, over cycles of tens and hundreds of thousands of years. Wally Broecker, one of the pioneers of paleoclimate science, famously called the climate system an unruly beast, and Milankovitch cycles are the slow hand on the leash. They do not push with brute force, but they guide the thresholds, nudging Earth toward states where ice can either flourish or fade. Yet there is a quiet humility in recognizing that these majestic cycles operate almost entirely outside human experience. A full tilt cycle is nearly twice the time since anatomically modern humans first walked the Earth. To Milankovitch himself, writing in the early 20th century, they were a matter of pure celestial mechanics, a way to understand past climates and perhaps to predict the slow drift toward future ice ages. For most of geological history, that was enough. The rhythm of ice and warmth was governed by orbits and feedbacks of ice, oceans, and atmosphere. But in the last 2 centuries, something new has entered the story. James Hansen, former director of NASA Goddard Institute for Space Studies, once wrote that humanity has become a principal driver of planetary change, comparable in strength to the great natural forces of the past. By digging up and burning carbon that had been buried for tens of millions of years, we have thickened the atmospheric blanket in a geological instant. Where Milankovitch cycles adjust the distribution of sunlight by a few percent over tens of thousands of years, our emissions have altered the planet's heat balance within the span of a single lifetime. This is where the story becomes both scientifically fascinating and morally unsettling. Left to itself, the present configuration of the orbital cycles might have nudged Earth slowly toward the onset of another ice age over the next tens of thousands of years. Summer sunlight in the far north would gradually have declined, favoring the survival of winter snow and the growth of ice sheets. Instead, we are adding so much heat to the system that the thresholds are shifted, the levers displaced. As the climatologist David Archer has pointed out, our carbon pulse may suppress the next glaciation entirely, holding the planet in an unusually warm state long after our own civilizations are gone. There is a strange irony in this. For centuries, humans felt dwarfed by the scale of cosmic cycles. The tilt of Earth's axis, the slow wobble of precession, and the breathing of ice sheets across continents. These seemed like forces so grand that nothing small and soft and mortal could ever alter them. And indeed, we are not changing the orbits themselves. The geometry of the solar system continues on its stately way. But by altering the composition of the atmosphere, we have changed how the climate responds to those orbital nudges, like changing the material of a drumhead while the drummer keeps the same rhythm. The beat is still there, yet the sound is different. To think about this in a meditative way is to sit with 2 truths at once. On the one hand, Earth remains part of a cosmic pattern that stretches, from the spin of planets to the pull of distant stars. The Milankovitch cycles remind us that climate is not a random walk, but a slow choreography between Earth and Sun. On the other hand, within that vast dance, there is now a brief, bright flare of agency. A species capable of reading the pattern and also disturbing it. When you picture future ice ages now, the image becomes layered. Somewhere far ahead in time, long after cities have crumbled and languages have changed beyond recognition, the tilt will again ease. The precession will again align seasons with certain points in the orbit, and the orbital cycles will once more favor snow that refuses to melt. Yet the timing, intensity, and very possibility of those distant ice sheets will carry the faint signature of our present choices. As Milankovitch traced climate in the quiet of his calculations, he could hardly have imagined that one day tiny beings on that same spinning world would heat the air and delay the snow. In the soft silence between numbers and orbits, you can almost hear the planet breathing. A slow inhale as ice advances, a long exhale as warmth returns. The cycles of tilt, eccentricity, and precession are like the pulse of a sleeper curled in the dark of space. Now another sound has joined that pulse, the crackle of our machines, the whisper of carbon rising. To understand Milankovitch today is not only to marvel at the celestial clockwork, but to recognize the delicate point in time where cosmic rhythm and human will intersect. Have you ever looked up at a constellation and wondered if the pattern you see is a lie told by time? We grow up thinking the stars are fixed markers on a cosmic dome, quiet lights that only rise and set while we spin beneath them. Yet, in truth, each star is a traveler with its own trajectory, its own story, its own secret path through the galaxy. The sky tonight is not the same sky our distant ancestors saw, and it will not be the same sky our descendants inherit. What we call constellations are like fleeting shapes in a river of light, and the river is always flowing. Astronomers have a gentle name for this subtle drift of the stars across the heavens. They call it proper motion. On human timescales, the stars seem almost motionless, but with patient measurement across decades and centuries, their slow crawl becomes undeniable. A star that appears nailed to the black canvas of night is in fact racing through three-dimensional space at tens or hundreds of kilometers per second. Only its distance makes that speed look like a tiny yearly step. Sir Arthur Eddington once remarked that observation is not just seeing, it is learning how to see change where the eye insists there is none. Proper motion is exactly that lesson, a reminder that stillness is often an illusion born from our impatience. To measure proper motion, astronomers return to the same stars again and again, marking their coordinates against a framework of more distant objects whose motion is smaller still. Over time, those measurements reveal tiny angular shifts, fractions of an arcsecond per year. If the night sky were a painting, proper motion would be the almost imperceptible smearing of the paint as the whole canvas slowly slides underneath our gaze. Some stars, like Barnard's star in Ophiuchus, rush so rapidly across the sky that their movement becomes obvious within a single human lifetime, a bright punctuation mark in an otherwise calm sentence of stars. But even the quieter ones are moving, threading their way through the galactic disk in a vast traffic of suns. Yet motion across the sky alone is not enough to tell us who these stars really are or where they live in the galaxy. To understand distance, astronomers invoke another subtle phenomenon, one that depends not on the star alone, but on the restlessness of the Earth itself. As we orbit the Sun, our viewpoint changes, and nearby stars appear to wobble slightly against the background of more distant ones. This apparent shift is called parallax. It is the same effect you see if you hold out a finger, close one eye, then the other, and watch your finger jump against the far wall. Space agencies sometimes describe parallax as the first true rung on the cosmic distance ladder, the place where geometry itself becomes our measuring stick. The angles involved are tiny, so small that for centuries they defied our instruments. Only in the 19th century did Friedrich Bessel succeed in measuring the parallax of a star with confidence. It was a turning point, proof that stars are not painted lights but distant suns spread across a deep volume of space. Since then, our tools have grown more refined. From early photographic plates to space telescopes like Hipparcos and Gaia. These observatories watch the stars from above the blurring atmosphere, detecting parallax shifts measured in micro-arcseconds. As the astronomer Kip Thorne once noted, precision is a form of courage in science. The willingness to chase meaning inside numbers that look almost impossibly small. When we combine parallax with proper motion, the sky ceases to be a flat map and becomes a living three-dimensional landscape. Information about distance tells us how bright a star truly is, whether it is a small lantern nearby or a blazing beacon far away. Information about proper motion tells us how it is moving through the galactic gravitational field, whether it travels with the disk, cuts across it, or perhaps belongs to the ancient halo that surrounds our Milky Way. Together, these two measurements let us trace the threads of stellar orbits, reconstructing the choreography of billions of suns in a kind of slow cosmic ballet. From this ballet, deeper stories emerge. We begin to see that some groups of stars share a common motion, likely born from the same long-dispersed cluster. We recognize streams of stars that are the tidal remnants of galaxies once swallowed by the Milky Way. We detect ripples in stellar velocities that hint at encounters with dark matter clumps or passing dwarf galaxies. In this sense, every proper motion measurement becomes more than a number. It is a fossil record of gravitational events written into the paths of stars. As the astrophysicist Vera Rubin argued about rotation curves, the motions of luminous matter are our most honest witness to the unseen. With enough stars measured, the galaxy itself begins to resolve before us, not as a photograph but as a dynamic model. We map spiral arms, stellar streams, moving groups, warps and waves in the disk. We can ask where the sun has been in the past and where it is likely to travel in the future, and even speculate how changing stellar neighborhoods might influence the flux of cosmic rays or the distribution of interstellar clouds around us. Carl Sagan once said that we are star stuff contemplating the stars, but with these measurements, we are also star stuff reconstructing the journey of its own galactic home. Against this background, constellations reveal their true nature as temporary alignments. Orion, Scorpius, Ursa Major. These familiar figures are formed by stars at wildly different distances, moving along different paths. Freeze time for a few thousand years and they look solid enough. But run the clock forward 1,000,000 years in a computer simulation, and Orion stretches apart. The Big Dipper S-handle bends and breaks. To future skywatchers, our folklore figures will be unrecognizable. The night sky is a storybook whose letters are slowly rearranging themselves, word by word. There is something quietly humbling in this realization. When a child learns the constellations, they are entering into a chain of memory that spans cultures and millennia. Yet beneath those shared patterns, the stars are carrying on with no regard for our lines and myths. Their true loyalties are to gravity and to the long-term dynamics of the galaxy. Our diagrams fix them, but physics frees them. To me, this tension between the stable map in our minds and the restless reality in the sky is where the poetry of astronomy begins. From a more practical point of view, proper motion and parallax are also tools for finding new worlds. Once we know the distance to a star, we can interpret the dimming of its light when a planet passes in front, or the tiny wobble in its position caused by an orbiting companion. These methods have led to the discovery of thousands of exoplanets, some roughly Earth-sized, some in habitable zones. Our maps of nearby stars are no longer just cartography for its own sake. They are treasure maps in a search for other possible homes for life. As the astronomer Jill Tarter has said, we are the first generation in human history with the tools to actually do this kind of cosmic archaeology in real time. There is also a meditative quality to this work. To measure parallax, you must wait for Earth to complete half an orbit, then another, comparing images months apart. To build a catalogue of proper motions, you must wait years, perhaps decades. The timescales of careful observation pull us out of the urgent rhythm of daily life and into a slower, more cosmic cadence. In that sense, the stars are teaching us patience, asking us to breathe with the orbit of our own world and to accept that real understanding often requires many journeys around the sun. Meditation teachers sometimes invite students to watch the breath as a way to anchor awareness. Astronomers, in their own way, watch the breathing of the sky, the slow in and out motion of stars as they shift against one another. Proper motion is the exhale, stars drifting outward across the firmament. Parallax is the inhale, our changing vantage point pulling them back and forth in tiny arcs. Sit with these movements in your mind for a while, and the night sky becomes less a ceiling and more a living being, expanding and contracting over eons. In the end, when we talk about the motion of other stars and the ways we measure them, we are really talking about our desire to know where we are and who we are in a universe that does not come with labels. Every angle measured, every parallax detected, every proper motion traced is an act of orientation. It is as if humanity, standing on a small moving rock, is quietly whispering to the cosmos, "Where are we going? Who is traveling with us?" And the stars, by their patient shifting, by their measurable wanderings, answer not in words but in paths, inviting us to read the galaxy as a great unfolding script of motion.